Okay, so I'm gonna go over several things here. So there will be the juicy video, the juicy demo that is coming toward the end. I will operate a little bit unusually because I'm gonna. I have two concrete demos to present, but which come in chronological order. But because of the sensitivity of the computation, I will have to restart the computer because it's a lot of frameworks that takes a lot of resources. So the two first elements that I wanted to present are just artifacts from the project. So the first one would be the impact map, basically, because we are experimenting BDD. So I produced the whole impact map that tried to address some of the concerns that you were mentioning, Viviane. So overall, I'm not going to go through the detail of it, but just to give a sense, and then if you want to look at it later. So basically, we can say that the whole, one of the main objectives here is increasing knowledge dissemination. The different persons that are impacted, the different group of users that are impacted are represented here. There's users, the catalog, the library in terms of cataloging area, maybe another area which is more SDR and so on. How does that impact, for instance, user? Well, to help contribute the goal, they need a quick and efficient way to find content. We need to provide them ways to find ourselves also on search engine and so on. And that's where you have semantic search that get into the play. Can I say that? Get into play. So semantic search relevancy is one of the features that we can develop to help the user find content faster. Semantic type ahead is another one. Info box is another one. I think you remember the meeting that we had. But you can also think about semantic content recommendation. There's a bunch of things that can be done. But the point is that once you get into the RDF model and semantic and so on, while originally the cataloging area here is MARC21, you end up having a situation where you need to handle two data models, right, in the same infrastructure. And that's what I call polyglot data management. And in that respect, one of the things that we are trying to build as a feature is a continuous scalable fault and fault-tolerant pipeline to help us move data from one data model to the other, right? And those are the different user stories, but you can, it's a little bit small, but those are the different user stories that we are working on. We started with the 36K Casalini record, which represents kind of partial dump, and that can be extended later to the entire cataloging. Then you have another specific case, which is to handle updates, okay? And what we are working on right now, the user story we are working on right now is the 36K Casalini record, the dump, partial dump, and then we're gonna, once that is done, we're gonna move into the update case, which needs more care because you have to maintain the order of the change that is happening in Symphony. So this will be shared later. So if you want to have another deeper look at it, will be shared later. Then we produce also, we have the architecture for this infrastructure that we're building right now. So as you can see, Kafka is in the middle, Spark and Kafka are the main component. Spark, basically Spark streaming is for the stream processing of the data. Kafka is kind of the backbone buffer through which the data flows. And we have the two cases represented here, the dump case, the streaming application for the dump case, where we can have full parallelization because the order in which we process the record does not matter. And then the other case is the update. And in this case, the order actually matter. And we use also some interesting component here, reactive stream-based component to produce data and to retrieve data. And this is the second demo that I will do because I'm first going to demo the whole thing, and then I will explain in detail what are those reactive stream components and how they are important for the infrastructure. Basically, you can process very fast with Spark and Kafka, but if you are slow at ingesting and digesting, you lose the whole point of it. So those are components that allow you to do an optimal use of the resource of the machine on which you are in terms of pushing the data inside the pipeline. So the demo that I'm going to do is not going to include Symphony here. Basically, this will be replaced by streaming data from the file system at that level. Then we have this application here, and we have a consumer that is going to write into Stardog. Right? So that's what the demo is going to be about. It's just not include Symphony at that point, but we have the whole thing until Stardog. Stardog being the triple store that we are testing. Okay, so like I say, we're going to stream the content of a folder which contains the 36 questionnaire record, push it through, and then get it into Stardog. If it works. So let's go verify. Kafka is up. Yes, we have Spark trimming is also up. Right? Yeah, 0. Nothing is going through. We have Stardog here. We make sure that it's empty. So I'm going to execute a command just to empty the data. So now I'm going to start the producer that is going to read the data from the folder and then stream them to Kafka, and then the whole pipeline will go, and we're going to start also the consumer here. This time it should work. If I copy to success, because the processing is happening right now, you can see that the machine is starting to lag a little bit, right?
Does the Stardog HTTP protocol provide any options to turn off indexing?
I understand the question, but those are two different concerns. The SPARQL-HTTP protocol is not Stardog specific, it's W3C specific. And the indexation is something that is provided as a plus by the triple store, which is they have a Lucerne indexer inside of it, but you don't have to use it. And indeed, I didn't disable it here. So does that answer your question?
Yeah.
Okay, so let's see what's going on here. Yeah, so it's getting 50 records. Like you have 16 parallel tasks, no, 12 parallel tasks right now that are receiving, batching 50 records and pushing them in the triple store. So now we can look at Stardog here and not execute that at all. And go in the browser and let's see if we have some agents here. Oh my God, the machine is dying. BIBFRAME people, does that ring a bell, what you see here? Stardog is kind of guessing the label to show and so on. That's an agent.
Yeah, it looks a bit insane, but that's probably on the converter and not necessarily on your pipeline.
So
well, there's no reconciliation or
exactly.
duplication going. So
exactly.
Instances.
It looked like
OCLC identifiers.
OCLC identifiers, like 300 Bs and like, yeah. Exactly. 33 pages. Cool, okay. So putting the data quality aside, we do see that you are able to run it into Stardog. We'll note that some of the craziness of the data is because this is not a work cycle to actually improve the converter, just to make those MARC to BIBFRAME converter run on this framework.
Just to say, this process, when I run it with my two laptops, just putting Spark on my node, on this node, Kafka on this node, and then Stardog on the other one to optimize Stardog because the database ingestion is kind of heavy, the process takes about 8 minutes to load the 36K record.
All right.
Without super optimization.